All right, everyone. In this video, we are going to overview resonance, do an overview on what resonance is, and look at the situations in which we see resonance occur. So first and foremost, when we conceptualize of resonance, what I want you to think about is that resonance is the delocalization of pi-electron density through an interconnected series of p orbitals. Taking this generic example up top here, imagine that you have a series of atoms all in a row that have p orbitals. When we have that interconnectivity of p orbitals, pi-electron density can flow through those p orbitals like electricity might flow through a fiber optic cable. Resonance is the delocalization of pi-electron density through an interconnected series of p orbitals, and essentially that means that the electrons have fluidity, okay? And because of that fluidity and the dynamicity of the flow, we might need multiple structures to accurately reflect the real compound. Okay, so we use resonance structures to depict where the pi-electrons go and where charges may be created as a result of that resonance. So here's kind of the crux of it. We can delocalize lone pairs that are existing in p orbitals or pi-electrons towards pi systems that could be double bonds or triple bonds, or towards atoms with empty p orbitals like boron, aluminum, or carbocations. When making 3 bonds, boron, aluminum, and carbocations all have an empty p orbital. But what we should never do is delocalize towards sp3 hybridized atoms because they don't have p orbitals. We should never break sigma bonds, and the overall charge needs to be conserved between contributors. So what we're now going to do is look at instances of resonance, detail that, and later on we'll do more examples with resonance. So to begin with, let's say that you have a lone pair atom, like oxygen or nitrogen, for example, lone pair atom that's connected through its sigma bond to a pi system. Well, that kind of looks sp3, that oxygen's actually sp2, and one of the lone pairs is going to be put in a p orbital, and the other is going to exist in a hybridized orbital. Because one of the lone pairs is put in a p orbital, we can delocalize that into the pi system. I can take that oxygen's lone pair, make a pi bond between the oxygen and the carbon, and then as a result of that push, I then need to break the pi bond. That then moves the pi-electron density onto that adjacent carbon as a negative charge. So I can delocalize a lone pair atom into that pi system. Notice because we're overall neutral to begin with, naturally as a result of resonating, I've created opposing charges, so I'm still overall charge neutral. Now, I've got this negative charge here, which is still a lone pair atom adjacent to a pi system, so I can continue to resonate that. I can make a pi bond going from my lone pair to the middle of the bond, and then I would break the adjacent pi bond. And if we're tracking together, notice that negative charge moves in a 1-3 relative fashion. A 1-3 relative movement if 1 is where the lone pair begins, then 3 is where the lone pair ends. I just like to track numerically at times. We move in a 1-3 relative fashion. Now that the negative is adjacent to this pi system, I can make a pi bond and break a pi bond, creating this structure here. And there's another additional contributor because I could make a pi bond there and delocalize back onto the oxygen atom. Now, the very last contributor and the very first contributor here, those are different from the standpoint that the pi bonds have just kind of been rotated around the ring. I've just shifted the pi bonds around the ring, and that would be a valid resonance structure. So first instance is a lone pair atom delocalizing into a pi system. Again, that could be a double bond or a triple bond. Later on, we'll look at examples where we resonate into a triple bond. Now, let's look at anion resonance. Anion resonance is technically still a lone pair atom adjacent to a pi system. That carbon of negative charge there has a lone pair. I can make a pi bond and then break the adjacent pi bond. Notice 2 arrows are required to describe that flow. And again, we're seeing that 1-3 relative movement. 1-3 relative movement. Then looking at the next contributor, because that carbon of negative charge is adjacent to the C double bond O, I can then make a pi bond here and break the carbon-oxygen pi bond. As a result of that flow, I'm making a carbon-carbon pi bond there and breaking the carbon-oxygen pi bond, leaving the pi-electron density from the C double bond O on the oxygen as a lone pair, charging the oxygen negatively. Now, what we also know is from the very first structure that we cannot delocalize this way. I can't resonate in that direction because I'd be delocalizing towards an sp3 hybridized atom. That is not possible. All right, now I want to acknowledge that anion resonance is very similar arrow pushing wise to lone pair atoms adjacent to a pi system because they're essentially the same context. Carbon of negative charge, there's the lone pair atom adjacent to a pi system. 2 arrows are required to describe the flow. Let's now imagine that you have a carbocation. Remember, carbocations have an empty p orbital, and when that's adjacent to a pi system, the pi system can be delocalized towards the positive charge. Specifically, to go from one contributor to the next here, I only need 1 arrow, and I'm going to go from bond to bond. Notice that's moving the pi bond between these 2 carbons, and we relocate the positive charge. And just like the negative charge, notice that there's this 1-3 relative movement, positive charge, if we define that as being at position 1. As a result of that arrow push, it moves to position 3, 1-3 relative movement. Now, this carbocation here is adjacent to that pi system, so I can go from bond to bond and relocate the positive charge to that carbon atom there. So notice that we're delocalizing towards the positive, going from bond to bond, moving that across the carbon skeleton. And when we're moving the negative, we need 2 arrows. First arrow goes from lone pair to bond to make a pi bond. Second arrow goes from the pi bond to the adjacent atom, breaking that pi bond and leaving it as a lone pair on that atom. Now, one of the more subtle instances of resonance is when we have a lone pair atom connected to an atom with an empty p orbital. A little bit ago, I showed you the atoms boron, aluminum, and carbocations. When making 3 bonds, those atoms are sp2 hybridized, and they have an empty p orbital. So while you see no pi bonds to begin here, we need to acknowledge that because the oxygen is directly bonded to that carbon of positive charge, what's possible here is that the oxygen can fold down its lone pair, making a pi bond to the carbon, in which case the oxygen has taken on the positive charge. Notice in this case, the relative movement of the charge is a 1-2 relative movement. That's because we're simply filling that empty p orbital, and so the oxygen is taking on that positive charge. One thing that's relevant to consider here is that the carbocation is itself incomplete octet, but as I resonate into the empty p orbital and the oxygen takes on that positive formal charge, I've now created a full octet structure, which is much more stable. Another example of that situation of a lone pair atom adjacent to an atom with an empty p orbital would be having a nitrogen with a lone pair connected to boron. For example, the nitrogen can resonate down from the lone pair to the bond between the nitrogen and the boron, and I can form a pi bond. Because we started off overall neutral, I'd have to create opposing charges because the nitrogen gave up electrons. It's becoming positive, and because the boron is the recipient of those electrons, it's becoming negative. So a lone pair atom adjacent to a pi system. Now consider that maybe we started here. This was the initial structure we were given. Because we have a polarized pi bond here, we could polarize that polarized pi system, pushing electron density onto the oxygen, giving it a lone pair, and making the carbon positive. So we can consider that this is a lone pair atom adjacent to an atom with an empty p orbital, and the reverse push is when you have a polarized pi system, and we polarize that pi system, we push up towards the more electronegative atom, creating a charge disparity, making the carbon positive. Okay. And for now, we're going to skip over radical resonance. Radical resonance we'll cover towards the end of the course. So this is an important prerequisite to any further discussion of resonance. Okay, we can delocalize lone pairs or pi-electrons towards atoms with p orbitals, with empty p orbitals, or towards pi systems, but we should never break sigma bonds. We should never delocalize towards sp3 hybridized atoms, and the overall charge needs to be conserved between contributors. All right, in the next video, we'll look at the orbital view of resonance.